Hi, it's time for another math easy solution. Time to discuss further into parametric equations and now look further at the laboratory project which I covered in my earlier videos, and now go over part 4 of the running circles around circles project, again where this project is just an interesting project at the end of each at the end of some of the chapters of my calculus book. And this is a very interesting one, and also useful tip again, if I'm going too fast or too slow, you can play this video at a different speed with YouTube, which is pretty cool as a setting in there when you watch on your computer. So anyways, in the earlier parts I went over questions 1, 2, and 3, and now we'll go to question 4, but before that, just to recap, we were dealing with a hypocycloid, which is just a curve sketched by tracing this point P around the circle that rotates around a outer circle, and you trace this around. It's going to look something like this, etc. So now let's go to question 4. And question 4 says, what happens if b equals to 1 and a is irrational? So recall from an earlier video that a rational number is just, well, when you can't write it as a fraction, and I'll put the link in description below. Can write as a fraction. And then the example we're stated to use is experiment with an irrational number like 2 to the power of 2 to the power of 1/2, or this is just square root 2, or e minus 2. That's an irrational number because e is irrational and you're just subtracting by 2. So this overall number is irrational. And again, where these b and a, those are the constants in this equation, these parametric equations, where a is the outer radius of this big circle, b is the inner radius of it. And these are parametric equations for the coordinates on that curve, like that. And then further into part 4 it says, take larger and larger values of theta and speculate on what would happen if you were to graph the hypocycloid for all real values of theta. Okay. And in other words, again, if you look at the curve, the theta, this just means you're rotating it around infinite times if you're taking it larger and larger values of it. So now let's write down our Q4. So for this question, we know that b is equal to 1 and a is irrational, like that. So what we have now is, well, if we a minus b, if we write a minus b, just so the equations have that, and this equals to, well, a minus 1. And so we have this figure, and we also know that a minus b over b, that's just going to be, well, a minus 1 over 1, and this just equals to a minus 1. So both these equal to a minus 1, and then we could throw that inside this equation, this a minus b over b, and it's a minus b over there. This is cosine, cosine. B is 1 and the y's have sine, so let's write that down. So we have x equals 2, a minus 1, like this, cosine theta plus cosine theta, because b is 1 here, no, cosine, not theta, a minus 1 theta, like that. And then the y's is going to be a minus 1 sine theta minus, now we have a sine, and now we have an a minus 1 theta, like that. So now we graph these equations, and if you recall from my earlier video on question 2, we had, well, b equals to 1, and then when we did this, in my earlier video, so it was the same thing here. We just made b equals to 1, and then we had what I showed in part 2 was that this was just a hypocycloid. So this is same as Q2 when I was graphing it and put it like that. And what we ended up getting was just a hypocycloid of this was a cusps, or the number of cusps was a, and remember the cusps were just the sharp points in the curve, and we'll get to that further as I graph these. Yeah, so now what I've done is, well, I've set up this another Desmos calculator here. It's quite an amazing calculator. I can't state it enough. It's just play around with it. It's quite amazing. So here I've inputted that a minus 1, and I put this for the square root 2, and we have a shape like this, but this just means we need to change this this range here of t. T is a theta. You can't put theta in here. In this calculator. And again, like always, the way to set up, you put the x and y coordinate, like that. Just assume fade st, and then I also put it here so that I could graph a single point. And this is the exact same formula as above, but instead of t or fade I put z so that I could change z by itself. And this one you could change a for whatever you want. So if you put square root 2, we have something that looks like this. So this means we need to change this up further. So let's just make this 4, and it goes a shape like that. Let's go from negative 4 pi. Now we have a shape like that. Let's go to 6, and it keeps going on and on. Let's go to 10. So there's a shape like that. Let's go to 10 to 10. We have a shape like this, and you could play this, etc. So as you can see, when we keep increasing it, you get crazier shapes. Now this is 123. Let's go 12, 123, and yeah, and in fact, if you were to change this up even higher, let's put another 0, so let's say 12,000. As you can see, it's getting a solid shape like that. Just because all this is covering everywhere when you have this square root 2. So what I've done here, I've copied and pasted several of those graphs. This is again for the a equals to square root 2 irrational number, and this is from negative 10 pi to 10 pi. And we get a shape that looks like this. And notice there's always this extra piece here. So the way it works is then it would go back to a different spot, etc. And here, and I've got it from negative 100 pi to positive 100 pi. And you could see a shape that looks like it's quite amazing. It looks like a black hole in the center. And now what I've done here, this one's for 200 pi, just to show you how it gets denser and denser. And again, this is from negative 1000 pi to 1000 pi, and it becomes an absolute solid shape here. Quite amazing. So now here what I've done is I've used a equals to e minus 2, and you get a shape like this. This is from 0 to 7 pi. Let's write that down just to show you 0, and this one is 7 pi. Whoops, let's erase the whole thing. 7 pi, like that. And this number here, you could just write e minus 2. So e minus 2 is about 0.7182, etc. And we have a shape that looks like this, and we need to update this range as well. 0, let's go to 7, like that. So play, and we have the shape going around it like that. So it's just cool, and you can speed it up. Yeah, this is the coolest calculator I've seen. So now what we'll do is if we increase this, let's go to, instead, let's go to 10. So we have a shape that goes around like that. So it looks something like that. And then let's go to 100. Now we have a shape like that. As you can see now, these cusps, so the cusps are these sharp points. It's on the inside now, and that's because a is, well, less than 1 here. Now if you put 1000, we have a solid shape like that, and it's getting more and more solid. You can still see some of it, but notice that the calculator becomes slower because it's just doing a lot of calculations. And yes, we get something like that. Let's go and see what I've done here. So I've screenshotted it, and this one is for a equals to e minus 2, like that. Yeah, whoops, just fix that up. So that's for a is equal to e minus 2, which is 0.718, where this is less than 1. Keep that in mind, because I will be changing some stuff. This is from 0 to 10 pi. Again, this is also, yeah. So yeah, that's 0 to 10 pi. This is from 0 to 7 pi. We have a shape looks like this, and it goes around there. And again, this is less than 1. So from 0 to 7 pi, we have that. And then when we go to 100 pi, we get something that looks like this. So you get more and more of these shapes. But as you can see, all the cusps are on the inside. And this is from 0 to 500 pi. Just to show you, it's getting thicker and thicker like that. Quite amazing. And then finally, when you have 0 to 1000, we get a shape that looks like this, which is just pretty much like a solid washer. So in general, for irrational numbers, if a is greater than 1, we get a figure with cusps on the outside ring. And you could also test it out with different irrational numbers. And this is cusps with the outside ring. That's again from our square root 2 number. So if we go to the square root 2, notice how all these cusps are on the outside like that. And that's because this number square root 2 this is greater than 1. And you could also play around with it, you'll end up seeing that. But then when it's less than 1, we have the cusps on the inside of the circle. So you can see all of them are on the inside. They're all on the inside here, like that. So And if a is less than 1, the cusps are on the inside rings, and then for greater than 1, it's on the outside ring. In any case, for irrational numbers or numbers similar to irrational numbers, as values of theta get larger, we get a figure that looks more and more like a washer or a solid washer, like that. If we were to graph the hypocycloid for all values of theta, hypothetically, at every point on the washer would eventually be arbitrarily close to a point on the curve. So it would just be completely filled out if you were to go to infinite number of thetas. And the following graphs show how drastically the curves look when we simply add a number to more corresponding decimal places. And this one, what I've done is I've got from a equals to 3, just to put a whole number like that. It's just a rational whole number. And then add a decimal place at 0.1. See how it changes like this. And I'll just go over here and do that. So let's write this here and write 3. So we have a shape like this. Is a full, it's like a triangle type shape. And you can, over here, let's increase this to 100. It's still the same exact shape. It just goes back and forth, so it's like a closed loop. And that's how the shape goes. Let's just slow this down. And now if you pause this, and let's make this 1,000, the shape remains the same. It's just a bit slow now because of the calculations. Okay. Yeah, and as you see, it's exact same shape when you have a whole number like 3. And now let's go add 1 here, just to make it a bit less, less simple, just a bit more complicated, putting a 3.1. As you can see now, there's random shape like this, but this is at 1,000, so this is the closed loop of it, and as if you add more and more to the, let's make the t or theta larger and larger, it's going to be the exact same shape like this. But now what we'll do is I will add a 2 to make this slightly more complicated. Now it gets to like that, and then eventually if you put a 3, which is still not a rational, I mean, this is still a rational number, just because you could write this in a fraction. You could just write 3,123, well, divided by 10,000 or so, or 1,000, I'm not sure, I'll just double check. But anyways, so that's the decimal place just stops. If it stops, it's not an irrational number. So as you can see, there's still some spots there, and if you put, let's say, a 4, and then see how quickly it now becomes almost solid, like that. And yeah, actually from 3 and 4 doesn't change too much, but if you erase, and just to see a tiny bit. But anyways, just to show you how much things change when you change, just add a few decimal places to a rational number. Let's go to 1, 0, just to make this faster. Yeah, just change it to 10 pi, so you get a shape like that. Anyways, so what I've done, I've copied and pasted that all here. Yeah, so what we have is at a equals to 3, we get a 3 cusps like that, 1, 2, 3. And now when we 3.1, we got a bunch of random cusps like that. And then you go to 3.12, it gets a shape like this, quite amazing. And then if you go to 3.123, and then it's pretty much like a solid shape like that. So basically, the more obscure, i.e. more irrational, and less patterns in the value of a, the more randomness in the pattern of the curve. Yeah, just put that in there, which allows it to look, actually allows it to move into more points on the curve, hence looking like a solid washer. So if there's more pattern, it's going to follow a specific pattern. If it's not, less pattern there is, it's going to hit more points in the curve. On the other hand, the more patterns or more simplistic a number, the curve obtains a distinct shape as shown below. Here I've got it at one point, this is 3.121212, and you get a shape that looks like that. This is quite amazing. So let's go to here and put this to 1,000. So here, and then this is just a bit slow. Okay, so 2, and it gets like that. We put a 1, and then 2, so it's a pattern. See now, notice how it changes. And then 1, and then 2. Once there becomes a pattern, it becomes simpler. So in fact, this is simpler than if you had 1, 2, 1, or 3.12, etc. And then we get a shape that looks like this, and this is 4, and you can keep going on and on. It's going to look exactly like this. So which is quite amazing. So basically, the more pattern in the shape, the more pattern in the numbers of the constants you use and the radius of the inner and outer radius, the more pattern in the overall curve. But then the opposite is true as well. The more irrational, the more sporadic, and then eventually solid the shape gets, because it hits every single point. Quite amazing. So, but even though there's again no, this is irrational, the pattern eventually becomes solid, it still looks like a really cool pattern like that. So overall, the pattern's still there, just different. Yeah, just a bit different, but it's still quite amazing. So anyways, yeah, I highly recommend you checking out the Desmos calculator, and yeah, hopefully you enjoyed this video on all these crazy curves. Yeah, parametric curves, and then later on I'll show is polar coordinates. They're one of my favorite topics in all of mathematics. That's actually one of the reasons I started doing math, just because I found those quite amazing. How you could have some of the craziest shapes with just formulas. So anyway, that's all for today. Hopefully you learn. Like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.